Yeah, it doesn't matter. Well, some people get real, like we should recycle, we should, The way I look at it is pretty simple. Earth, sun. And eventually that sun is going to die, so it's going to expand. That'll be its first phase of death, is they'll expand first, and it's just going to pretty much swallow up everything out here. It'll all be recycled. So, yeah, in the long term, if we have trees now, trees later,
Take that out.
All right. So plus, I have a really poor attitude when it comes to the whole recycling and clean energy thing, because caring about the planet in general, because should we get political? We shouldn't get political in this class. Do we really care about this planet? I mean, honestly. We pay athletes. I was just running some numbers last night. I was watching the Spurs game. Do you know how much Kawhi Leonard made last night? Just last night.
Probably made
Before taxes.
80,000.
About $290,000. Okay? If you just take his salary and you divide it by 82 games. All right? We value the wrong things. In order to really take care of our planet, we have to value research in physics, which originally I was a physics major, but that's pretty much a dead-end science because you don't have enough money being pumped into that discipline to get you to the places you need to go to advance our cause, right? We eventually have to get off the planet. Like, we do have a finite amount of time here. But since we don't take it seriously, why should I take anything that anyone wants to do seriously? Now, maybe because selfishly I want to extend my life and my kids' lives, but eventually, if we're not going to take it serious, it's not going to matter long term, right? So that's why I just have this real, who cares attitude, because we need to be valuing the right things in order to be taking that sort of issue on. But hey, who am I? All right, back to this. Sorry about that. Whoa. Get back to this. Stick to what you know. All right, so this, I'm going to go, just rewrite this, e to the r. You're free to disagree, okay? If you disagree, fine. What's this going to be here? Plus 1? We're going to start running some problems now. We haven't had anything yet that's been like this. Do you see where the problem is? Just look at this right here. And let's actually just focus all of our attention on that. What we're trying to do is the limit as t goes to negative infinity of e to the t times t minus 1. And I'm not even taking the negative into account. I'm just looking at that. What happens as t goes to negative infinity? What does that thing turn into? 0, undefined. Well, let's talk about what's happening. What's happening to this piece? That looks a lot like e to the negative infinity, if that makes any sense. E to the negative, what the heck does e to the negative infinity mean? That kind of looks like 1 over e to the infinity, right? Negative exponent, you drop it down. What happens here? As we let t go to negative infinity, we're basically getting something that looks like this, which is a fixed number over a number that's getting huge, and that should go to 0, right? So at the end of the day, this thing is headed towards 0, right? Times, that's multiplication. Now plug in, let's see, negative infinity, take away 1, still negative infinity. So you have negative infinity. What is 0 times negative infinity in a limit like that? 0?
Or negative infinity?
Is it indeterminate?
Yeah, this is an indeterminate form. That's what we call an indeterminate form. There's all sorts of indeterminate forms from Cal 1. This is why I asked about, have you seen L'Hopital's rule? What are the indeterminate forms? What are the forms of limits from Cal 1 that when we see them we go, crap, we've got to do something? 0 over 0. Infinity over infinity. 0 times infinity or negative infinity, doesn't matter, plus or minus. What else? Yeah, like negative or positive. It doesn't matter. This can be plus or minus, plus or minus, plus or minus, plus or minus.
0 over infinity.
0 over infinity is not an indeterminate form. 0 over infinity goes to 0 because the numerator is getting small. Denominator gets big, but when your denominator gets big, it forces a fraction to get small anyway, so it's kind of like helping this happen. Other way around, won't happen. This will actually become infinite because anytime your denominator gets small, your fraction gets big. And the numerator is already trying to get big, so they just help each other out. So these are not indeterminate forms. 1 to the infinity is another one. 0 to the 0. Infinity to the 0, not infinity to the infinity. Infinity to the infinity would be infinite. So this is why I suggest that you go back and perhaps review the indeterminate forms from Cal 1, because we just ran into one of them, and this is it right here. So does anyone remember? I should call on my Cal 1 students. What's that?
You redo it again till it doesn't equal.
How do you mean redo it? Yeah, no. So
Yeah.
derivative is going to come in. L'Hopital's rule is going to, but what do? You're going to take one of the two factors, right? Anytime you have 0 times infinity, you pick one of the factors and you drop it to the denominator. And you create a ratio. So you get to pick. You get to pick. Which one would you rather drop down? E to the t and drop it down, or take this and drop it down? Your call. Let's do the e. So I'm going to rewrite this. T goes to negative infinity. I'm going to rewrite it as t minus 1 on top, and on the bottom I have to rewrite it as e to the negative t. Isn't that the same exact expression? But now that it's written this way, take a look at what happens. If I now let t go to negative infinity again, what does the numerator head to? Negative infinity, right? And now take a look at this piece right here. Where does that go? Let t become closer to negative infinity. So you're plugging in a negative number right here, right? Negative and negative is positive. So this really looks like e to the positive infinity down there, doesn't it? E to the positive infinity goes to infinity. And now you have a ratio infinity over infinity. And that's what you want, because you can only use L'Hopital's rule if you have what? L'Hopital is only valid when you have what? Infinity over infinity or 0 over 0. Those are the only two ways you can have it. Have L'Hopital. Can't use L'Hopital if you don't have these. So all those other indeterminate forms I showed you earlier, you would have to turn them into this before you could use L'Hopital. All right, so now that it looks like I can use L'Hopital, I actually need to use L'Hopital, so you can either write an L here or an H here. Different books, different people do it different ways. I like to write an L. That just lets me, when I'm going back to look at my work, know what I did, and it lets other people know what I did. I'm using L'Hopital's rule. And L'Hopital's rule says all you have to do if you have one of these forms is what? Derivative of the top and bottom separately. You don't do quotient rule. You just take derivative of top and bottom separately. So what's the derivative of t minus 1 with respect to t? Just 1. And then what's the derivative of e to the negative t? Negative e to the negative t. We have a little chain rule that we have to worry about here. Derivative of e to the negative t is itself, but then derivative of what's up here is negative 1, so it pops out. And that's our new limit. And we go again. We try and take the limit. T goes to negative infinity. 1 doesn't go anywhere, right? So now it's headed to 1 over, and then we just did this a second ago. Negative goes in here, negative and negative is positive. E to the infinity, and then negative. So the bottom is headed to negative infinity, right? A fixed number over infinity goes to 0. That goes to 0. So I'm doing like all this is like scratch work here, just trying to figure out what the heck's going on. If you were to like have the solution manual for the book and you were going to go and like read it and go through one of these problems, they would just go completely from here to like 0. They won't show you any of those intermediate steps. All right, are we okay with that piece? Sure? Yeah, let's look at the other one. No, the other one does not work out that way. It's going to be a little different. So here's where I am. This right here becomes, I already took the limit of this, right? And this piece right here just went to 0. So all I have is -1. Plus, now I have not addressed that one, so let me go ahead and now focus my attention here. And you're not going to be happy with me. Okay, what happens here? R goes to infinity. What's e to the infinity headed towards? Infinity. And then times infinity minus 1. Infinity. What's infinity times infinity? Infinity squared, which is infinity. That's not an indeterminate form. This is infinite. Plus 1, still infinite, right? No, this is infinite. This right here is becoming an infinite thing, right? So this is really like -1 plus infinity, right? -1 plus infinity, which means infinity, which means that this thing diverges. Which means that if you would have noticed this first and done this one first and seen that it went to infinity, you could have avoided having to do L'Hopital's rule. But what you would get mad at me if I did that and then on your homework you had a problem where you had to use L'Hopital's rule, right? Because I wouldn't have shown you that you need L'Hopital's rule. So if you ever have an integral that you split up into two limits like this, if one of them diverges, the whole thing diverges. All right? If one goes, it all goes. We're done. All right. Questions, comments, concerns? Concerns for the planet? No? No one has any concerns for the planet? Ow. Shit. That's karma. Yeah. I used to believe in mankind. I really did. I had high hopes. All right. This is not an example that you have to work out. This isn't something I'm going to test you on. But you know, as a student, it might be worth talking about, like, why would we ever want to actually look at the area under a curve between negative infinity and infinity? And this is a very famous example. It's called the standard normal, well, the normal distribution. This is a function. It looks pretty ugly, doesn't it? There's like a 1 over square root of 2 sigma pi, and then e to the negative x minus mu squared over 2 times sigma squared. Okay, what? Well, if we graph this function, it'll look like this. It is the bell curve, yes. It is the bell curve. And I think a lot of us have seen that before, but don't really understand like what it means and like how would this tie into this whole integral thing. So I'm gonna illustrate this with something a little bit more basic and then build to that. So in statistics, there's called discrete variables and there's called continuous. Not the continuous that you're thinking from calculus, all right? Like continuous functions that you draw without picking up your pencil. They are connected, but don't be thinking that right now. Discrete variables. Let me give you an example of a discrete random variable. The number of students in this classroom right now. Or let's say on any given day, the number of students in this classroom. What values can that take on? Integers, right? There could be no one in here, 1 person, 2 people, 3 people, right? There are integer values that could happen. The number of people at the Spurs game. Another example, right? If I roll a die, 6-sided die, How many outcomes? 6. 1, 2, 3, 4, 5, or 6, right? Those are discrete random variables. Then you have something like a continuous variable. Can I borrow your water?
I don't want to spill.
I was going to have some.
Oh, I'm sick.
It's all right. I'll be all right. We're all going to die. No, I'm kidding. So, so look, this says this says 20 fluid ounces, right? So let's say I take like 100 of these, and we start with this really precise measuring device, pouring out the 20 ounces of these 100 bottles and measuring them. Are they all going to be dead on 20? No. We might have one that's like 20.0015, right? We might have another one that's maybe 20.9034. See, these values can be 20, but they can also be a little bit more than 20, a little less than 20, any values, right? These are called continuous random variables. So let's go back to the discrete. Let's take the die, for example. If I roll a die, what's the probability of getting a 1? 1 out of 6. What's the probability of getting a 2? 1 out of 6. So if I were to graph that, I would have something like this. 1, 2, 3, 4, 5, and 6. Those are the values that could come out, right? So these are my values for rolling the die. And over here, this is my probability. So what was the probability of getting a 1? 1/6. So here's 1/6, right? So I could put there. And then here, they all have equal probability, right? Then what I could do is I could say, well, what's the probability, what is the total probability of getting any of these? So when I roll a die, what's the probability I'm going to get a 1 or a 2 or a 3 or a 4 or a 5 or a 6? 6 out of 6, right? 1. 100%. That 1 means 100%. And the way I can visualize this is by looking at these as being little areas. So imagine that I took, like go halfway, go up and draw a rectangle, up and draw a rectangle, up and draw a rectangle, up and, oh, I missed it. Draw a rectangle, up and draw a rectangle, up and draw a rectangle. So the distance from here to here is 1. Got it? Distance from here to here is 1. Distance from here to here is 1. Yes? What's the area of that rectangle? 1 times 1/6. So the area of that rectangle is 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. What we know from statistics is that in a probability distribution, which is what I just drew up here, the sum of all probabilities must be 1. And you can see it. The sum of all these areas is 1. Now, if we have something like your bottles, right? Your bottles, let's look at that. The bottle we just measured, right? Here's the values it could take on. Well, let's say here's 20. That's what they are advertising, right? As the manufacturer says, that's what's going to be in there. Now, do I say that at 20, the probability that's going to be 20 is 1? No, look, it's not, there's a good chance it's 20, but it's not, because there's going to be variation. There's no machine out there that can produce a bottle that has dead on 20 ounces. There's just no way, right? So I can't say the probability of it being 20 is 1. I have to be less than 1. Now, what's the probability that it's 21 ounces? Lower, right? What's the probability that it's closer to 20? Probably a little higher. It's probably a higher probability that you're in here, right? And you might be a little bit less over here, yes? Now, what's the probability that you have 0 in there? Probably no probability of that, or else you don't have a bottle in your hand, right? What's the probability that you have 30 ounces in there?
Considerably less.
It's low, right? Very low. Well, the container can only hold so much. But this is more to get you thinking conceptually here. The idea would be that these probabilities would drop off rapidly and go infinitesimally out to 0, but never actually be at 0.
Even though it couldn't?
Well, the bottle thing, we have a volume that's finite, so, But again, it's more the idea. Let me give you a different variable that would make a little more